Hey everyone, welcome again to new tutorial. In this tutorial, we're gonna analyze, as you see, occurrence relations. Firstly, what actually that is, the occurrence relation. It's just equation, It's equation that define a sequence based on the previous terms, the sequence. What does it mean? So if you want to find the expression for the current element, okay, if you want to find expression for the current element, which is an, that means the value of the current element depends on the value of previous elements. Okay, this is like the very good example is Fibonacci numbers, where you add, for example, if you want to find the Fibonacci number, 2-second Fibonacci number, you have to add the values, not the values, but the first Fibonacci number and the Fibonacci number at the zero index. If I remember, it was like that: fn equals to fn minus 1 plus fn minus 2, and if you want to find f3 is the third, actually this is the first, because the counting in computer science starts from the zero. But what I mean is that it depends on the value of the f1 and f2, right? So this is the case. This is also recurrence relation. Okay, because this is a sequence where the value of the current element depends on the value of previous elements. So have to solve them. But before going actually the problem solving case, I want to say you that there are two types of recurrence relations: homogeneous and non-homogeneous. So first one is homogeneous. I'm gonna write homogeneous recurrence relation. Homogeneous recurrence relations are relations that doesn't depend on any other constant term. What I mean by this is that it depends only, okay, let's say only on its own elements. The example is the example that I wrote about here. This is also, homogeneous. This is homogeneous because depends only on the previous element. The element of the terms of the sequence. Okay, it's nothing else there is. But non-homogeneous, as you might already know or understand, depends both on elements, own elements, and outer functions, external function. Function. So, for example, this is homogeneous. an 2a minus 2 and plus an minus 1. So this is homogeneous because both these elements are elements of the sequence itself. Okay, so what about this non-homogeneous? For example, this may be, okay, let me copy this sequence above, but now I am, which color to choose? Okay, green. I'm adding this, not a, but 2 to the power n. You see, this is what? This is external function. It's not the part of the sequence actually. Okay, this is not the previous element, this is not the next element, this is not n plus 1, this is external function, and this is the case of non-homogeneous recurrence relation. It may be any polynomial or exponential function, doesn't matter. Here we have fn, or let's say not fn but gn, okay, external function. So in this tutorial we're gonna see how to solve homogeneous. Firstly, okay, homogeneous recurrence relations. So solving homogeneous recurrence relation. So Okay, let's assume that we have this recurrence relation an 6 an minus 1 minus 9 a, not n but a n minus 2, and you're given initial cases. A0 is 1 and a1 is 6. So how do you solve homogeneous recurrence relations? You use a characteristic equation. Okay, so you're gonna use characteristic equation and use characteristic equation. So let me write the template or the format. C1 xn plus C2 x2n plus ck xk, right? xkn. So this is your characteristic equation, where, as you may know already, x1, x2, xn, xk not n, are roots of the equation, okay? And c1, c2 are just the constants, ck constants. So now we have what? Now we have this one, the recurrence relation. At the end, we want to have, or we will have, this type of characteristic equation. So that means what? For example, if you want to find a1, okay, you're gonna substitute and with the 1, okay? So it's gonna be c1 x1 1 in the power of 1, okay? Or let's say we're gonna find a2. So instead of 1, you put 2, okay? So you take the power 2 of each root, okay? As c2 x2 2 and so on, okay? So I hope it's now understandable for you. So now you know what format, or in what format we're gonna have the answer. So now our task is to kind of build this characteristic equation, and for this we need what? Of course, x. What is it's the root. So you do, or you solve in this fashion. So okay, we have what? an 6 an minus 1 minus 9 an minus 2. So I'm gonna move this everything the left side to the left side, everything in the right to the left. So I'm gonna have an minus 6 an minus 1 plus, okay, 9 an minus 2 equals to 0. So of course, in order to find the root, you're gonna transform it to polynomial equation, okay, to find what? X roots. Let's say set of x, because there may be more than one root. So I think it's very easy to transfer. I mean, let's say transfer, convert, I don't know, okay, convert. I think it's pretty not so difficult. For example, I'm gonna give you the tip. So here the least, let's say element, or not the least element, the element with the least, the smallest coefficient is gonna be just 1. What I mean is that it's gonna be constant. So you know, polynomial equation has this kind of format, cn, right? Let's say cn xn plus cn minus 1, okay, xn minus 1 plus, and finally you have what? C0, right? X 0 equals to 0. So this what? X in the power of 0 is gonna be just C0, right? So actually, yeah, x to the power of 0 is gonna be C0. So what I mean is that the least coefficient, not the least coefficient again, I mean the element with the least coefficient is gonna be C0. So in this case, this one is gonna be C0, right? I mean, in this case, our C0 is 9, right? And our x is what? Our x is an minus 2, but x here in the power of 0, so we have just 1, okay? So while converting the recurrence relation to a polynomial equation, firstly, please identify what's gonna be your C0. So now in this case, it's gonna be 9, and because 9 is a coefficient of the element which has the smallest coefficient. So now while converting this to the polynomial function, I'm gonna write here just plus 9, not this one. I won't write this because it is in the power of 0. Again, this is gonna be just 1, so don't need to write. So now our xn is gonna be what? Our xn is gonna be this one. So what's gonna be our n? Our n is gonna be what? Our n is gonna be 2, because we have 3 elements, right? This is in the power of 1, because here we have 0. This is gonna be in the power of this is in the power of 0, because here there's a 0. So firstly, you identify what's gonna be the C0, and then you kind of identify the power of each element. So this is gonna be in the power of 1, this is gonna be in the power of 2, so I'm gonna write here x in the power of 2. There is no coefficient, there's no C coefficient, there's just 1, so this is just x in the power of 2. So plus, I'm gonna, not plus, sorry, minus 6x in the power of 1, so just x, right? Because this element has the power 1. So yeah, now we converted our recurrence relation to a polynomial equation. I think it's very easy for you. I just made it so long to explain you how to convert them when you have a little bit complicated recurrence relation. So you find you identify what's your C0 firstly, then do you assign the powers, right? Do you assign the power to each element in the sequence, this case. So let's solve this polynomial equation, right? Let's solve it in order to find our roots. So this is gonna be what? X to the power 2 ax plus 9. This is nothing but x minus 3 power of 2 0. So we're gonna have now here just one root, which is 3. Okay. Yeah, we're done. We found the root, and the reason why I'm considering this example is that you might have just one root. In this case, okay, here now we're having only this part, right? Why we're considering this part? Why we're considering x1 and x2? Because, as you know, typically in second order polynomial equation, you're gonna have typically 2 roots, okay? So thus I'm considering only this part. I'm ignoring the rest of the part, okay? So firstly, let me copy this one, okay? Let me copy this one to below. So our an is gonna be what? C1 x1n, so plus c2 x2n. This is a typical equation when there are 2 roots. There are 2 roots, in, of course, second order polynomial equation. But if you have just one root, like in not linear algebra, but like in engineering mathematics, if you remember differential equations, when you have one root in a homogeneous equation, you add what? You add here n, okay? N to the power 1. Okay? For example, later you may see a recurrence relation, and when you convert it to polynomial equation, you may end up with third order polynomial equation, and in that case you will have three roots, but in that case you may also have two roots, one root and two the same roots. In that case you will have also this one, right? C3 x3n, but you have one root which is the same. Okay, I mean, typically in third order polynomial equation you will have three roots, but you have two roots. In that case you add n here in the second position and n to the power 2. Okay, I hope you got the idea. But for second order polynomial equation, if you have one root, let me delete everything here, you add just n to the second element in the characteristic equation. So what we're gonna have is that an c1 x1 n plus c2 n, okay, n x2 n. This is in the case when there is only one root. Simple as that. So now let's write this an. So an is equal to c1. Our root is what? 3 to the power n plus c2 multiplied to n multiplied to 3 to the power n. So this is not the end, because you have to find the value of coefficients c1 and c2, and for this you have the initial cases value. So you have these ones. We're gonna use them. Okay, so a0 is 1, a1 is 6. So I'm gonna substitute 0 to the place of n. So a0 equals to c1 multiplies 3 to the power 0, right? Instead of n, I'm putting 0 plus c2 and multiplied 3 to the power 0. And a1 and everything here equals to 1, right? Because a0 equals to 1. So consider this one. Okay, so if you have any kind of questions, please feel free to ask in the comment section. So a1, it's gonna be c1 to the power 3 to the power 1, because here we have n, our n is 1 here, plus c2 and 3 to the power 1, and this equals to 6. It's given. Okay, so you need initial values for what? To find the coefficient. This is everything the same like in engineering mathematics, like solving differential equations. Pretty easy. So now we solve this system of equations. Okay, so we have what? Sorry. I forgot one thing. Here, not n. Instead of n, we have what? 0. And here, also instead of n, we have 1, right? I just forgot to substitute here. So then what we have is that from here, from the first one, we have 3, not 3, but 3 to the power 0 is just 1, right? So 1 multiplied to c1, just c1 plus 0 multiplied anything is 0, so I'm not gonna write plus, I'm just gonna write that c1 equals to 1. So from the second, from the first one, from the second, we have this system of equation. 3 to the power 1 is 3c1 plus 3c2, right, is equal to 6. We know the value of c1, this is 1, so 3 multiplied 1 plus 3c2 equals to 6, so 3c2 equals to 3. Because I'm moving it to this side, it's gonna be minus 3, so overall c2 is also equal to 1. So now we can substitute the c1 and c2's value in our characteristic, not characteristic, but in our final result. So our final result is gonna be what? It's gonna be a n, okay, a n, everything is 1, right? Instead of c1 I'm putting 1 multiplied 3n plus 1 multiplied n multiplied 3n, so this is gonna be 3n plus n, 3n. I'm taking 3n out of the bracket, I'm having 3n multiplied 1 plus n. So this is your final result. So this is how you solve homogeneous equation. Firstly, you convert the homogeneous recurrence relation to polynomial equation. So we use characteristic equations. This is a template, right? This is a template. So I also explained how to convert to a polynomial equation. Firstly, you but you identify what's your C0. Once you identify your C0, then you assign the power to each element in the sequence, like here. So then you write your polynomial equation. You solve your polynomial equation. If second order polynomial equation has typically 2 roots, third order 3 roots, but in the case of if you have just 1 root in second order polynomial equation, you add this n, you multiply second root to the n. In the case of third order polynomial equation, if you have 2 roots the same, then you add to the second root n, not add but multiply, and to the third root you multiply n to the power 2, and so on and so on. So because we found only 1 root, our equation has only 1 root, we're using not this one. This is typical, right? As I've written for 2 roots, we are using this one because this is a template. This is a format that you use for 1 root because we add here n. So then we substituted our x with a 3, but in that case we needed also to find c0, c1 and c2. For this we had our initial values a0 equal to 1 and a1 equals to 6. So we need these values to find at the end of our solution our coefficients. We we found a0. I mean, instead of n we put 0, and we got 2 equations. I mean, instead of n we put also 1, so we got these 2 equations, and simply we solved these 2 equations and found the value of c1 and c2, which are 1s. So finally we substituted these values here, I mean, and finally we end up with our final solution, which is this one. This is how you solve homogeneous equation. In next tutorials we're gonna analyze how to solve non-homogeneous equation, but the idea is the same. In non-homogeneous equation, you firstly solve the equation, recurrence relation for homogeneous case, considering g0, okay, external function 0, and then you find a particular solution. Okay, so this is a homogeneous part, like in EM. Then you find particular solution, and your final solution will be the sum of homogeneous and particular solution, and you will have general solution. This is the end of our tutorial. If you have any kind of questions, please feel free to ask in the comment section.